Okay, so now we are going to look at something called the Wilcoxon-Mann-Whitney test. This falls under what we call a non-parametric test. So this is, I guess, Chapter 7, Section 10. Okay. And here we've got two samples of independent data. And so far we've been doing, the t-test, okay? And a key part of the t-test is that we assume that the sampling distribution of y bar, or at least, y bar 1 minus y bar 2, that comes from a normal distribution because of the central limit theorem, right? So kind of the mathematical underpinning the mathematical theory behind a t-test says that the sampling distribution of y bar follows a normal distribution. Okay, and this is basically based on the central limit theorem. Okay, and the central limit theorem says, well, in order to use the central limit theorem, there were two conditions. Okay, and basically the conditions to use the central limit theorem were, okay, samples must be selected independently and randomly. Okay. And the other was that the samples had to be large enough. Okay. And kind of our, at a practical level, this often meant you had a sample of 25 or more, 30 or more, okay? So in most cases, n greater than or equal to 25 is large enough, okay? But we might be in a scenario where we don't have a sample that's large enough for us to comfortably use the central limit theorem and assume that y bar follows a normal distribution, okay? So sometimes we're in situations where our sample is not large. Sample is less than 25, okay? And maybe outliers are present. And some potential outliers are present. Okay, indicating that the population is not normal. Okay? Because if the population is normal, then it's no problem if our sample size is small. Okay? And then we also saw that if the population is not normal, if our sample size is big, we also get that, normal distribution, central limit theorem still applies. Okay? But there might be the situation where the population is not normal and we have a small sample size. Okay? So if we're in this situation where our sample size is small and maybe some outliers are present, and because outliers are kind of an indication that we don't have normal data, then we might have to turn to something called a non-parametric test. Okay? So in these situations, we might use a non-parametric test. Okay? Now you can take an entire course on non-parametric tests. If you're, a researcher, you can research non-parametric tests and spend your entire career developing them. Here we're gonna spend maybe 20 minutes, and we're gonna learn one non-parametric test. And this is just kind of like, this thing exists, this world exists in statistics as well. And so we'll give it a little bit of attention, but we're not gonna spend a whole lot of time on it, okay? So the key thing about non-parametric tests is that it does not make any assumptions about, what the sampling distribution looks like, okay? So the central limit theorem, we're saying sampling distribution looks like the normal distribution, or we can relax it and use the t distribution, but we're basically using these mathematical distributions, okay? Non-parametric tests don't do any of that, okay? So, and we call them non-parametric tests because we don't use any parameters like the mean of the population or the standard deviation of the population. We don't really make any assumptions about the distribution of the population, okay? Non-parametric tests do not make any assumptions about the distribution of the population. Okay. All right, and so because of that, in general, non-parametric tests are less powerful than parametric tests. Okay, so non-parametric tests are less powerful than parametric tests. And what that means is basically you need more data to come to the same conclusion. Okay, so in general, you need more data to come to the same conclusion because you're not making any assumptions, and so for you to kind of come to a conclusion, requires more evidence, right? If you have strong assumptions to begin with, a little bit of data might be enough to kind of you have a lot of assumptions, the data comes in and you kind of go with them and you say, all right, well, this is what I'm going to conclude, right? So, in life, we often say it's not good to make assumptions about people based on first impressions and stuff, but it's actually a very useful and handy thing to do, right? And just we don't have the luxury of spending hours getting to know every single person individually, and so you have a 5-minute interaction, 10-minute interaction with someone, and based off of that, you make an assessment about that person and stuff. So anyway, but non-parametric tests, we're not making any assumptions. So in general, we need more data to make, to come to the same conclusion. Okay. But you'll want to use a non-parametric test when it's not safe to make these assumptions, right? If it's nice mathematically, the central limit theorem is really handy. Okay, when we can say, oh yeah, sampling distribution of y bar follows a normal distribution. That's a really nice assumption that we can make. But sometimes it's not true. We saw, I think when we did all of the simulations, we saw a lot of sampling distributions while n was less than 25, where it had all those peaks and spikes and had all these weird shapes that were clearly not normal. Okay, and if we had assumed it was normal, then all the p-values that we conclude would be wrong, and our conclusions would likely be wrong. Okay, so we would get ourselves in trouble by assuming too much. So non-parametric tests are useful in this case. Okay, so the one non-parametric test that we will learn in our class is called the Wilcoxon-Mann-Whitney test, also sometimes called the Wilcoxon rank sum test. Okay, so we will learn just one. Okay, it's known as the Wilcoxon. This is three people's names. Wilcoxon-Mann-Whitney, or the WMW test. Okay, mathematically equivalent. Something called the Wilcoxon rank sum test. All right, so let's just get into this. Okay. Okay, so I'm just using the example straight from the textbook. Okay, and in this example, we are looking at soil respiration data. Okay, so I guess in certain sciences, you can go out and collect data on how much carbon dioxide the soil gives off. Okay, and so they went to a forest and they looked at two areas. One where there was lots of, so they gathered data from an area with lots of growth, and an area where there was a gap. Okay. All right, and so I'm going to just kind of list this out. So we have growth numbers. So this is, I guess, I don't know, certain amount of carbon dioxide growth versus gap, and this is arranged from least to greatest. Okay, so the numbers 17, 20, 22, 64, 170, 190, 315. Just Okay, and then on the other side, 6, 13, 14, 15, 16, 18, 22, 29. Okay. And, okay. And what we do, our hypothesis, our null hypothesis, is something along the lines of both areas, the growth and gap area, tend to produce values from the same distribution, okay, or produce values that come from the same distribution, okay, so this will be both areas, that is the growth and gap, produce values from the same distribution, okay? The alternative hypothesis, okay? So if I do a directional, so one thing to note is for non-parametric things, you have to write out the hypotheses because there's no parameters. You can't talk about mu, like the mean of the population, because that's the opposite of non-parametric test because you're talking about a parameter. So there's no parameters in the hypotheses. So the directional alternative will be something like the growth area tends to produce values that are larger than the gap area. Larger values than the gap area does. Okay. A non-directional alternative would be one area tends to produce larger values than the other area, but not specifying which. One area, but not specified. Tends to produce larger values than the other area. And the other area does. Okay. Okay, is that all right for the hypotheses? So we're saying, you know, in this case, we're saying the growth numbers tend to be larger than the gap numbers, or one area tends to produce larger. Okay. All right, and this is a case where, you know, when we look at it, you know, we've got a small data set, 1, 2, 3, 4, 5, 6, 7 numbers from the growth area. And if we look at these numbers, we're like 17, 20, 22, 64, and then we got numbers like 190 and 315. And so maybe these are outliers, or this just, it doesn't seem like they're coming from a normal distribution, okay? You know, maybe the gap numbers, the gap areas, there don't seem to be numbers that are like extremely large or small, so maybe those come from a normal distribution, but the growth numbers, certainly it doesn't feel like they're coming from a normal distribution. And because we only have a sample of like 7, it would make us uncomfortable to assume that the distribution, you know, sampling distribution is normal. Okay. All right, so what we do is with our numbers is we count the values in the other column that are smaller than the current value. Okay, and ties are worth 1/2. Okay, so I'm going to go ahead and do that. All right. So I say for 17, how many values in the other column are smaller? So 6, 13, 14, 15, and 16. I've got 1, 2, 3, 4, 5 values in the other column are smaller. Is that okay? At 20, I can count 6, 13, 14, 15, 16, and 18. I got 6 values in the other column that are smaller. 22, I've got 6 values that are smaller, and then there's a tie at 22. Ties are worth 1/2. So I'm going to write 6.5. Okay? And at 64, 1, 2, 3, 4, 5, 6, all 8 values in the other column are smaller. Is this okay, what I'm doing? All right, and then I do the same. Is this confusing? Okay, so I'm going for each value here. Okay, so for each value, I count how many values in the other column are smaller, right? So 17 becomes 5. So there are 5 numbers in the other column smaller than 17. So I say, here's 17. How many values are smaller than 17? Okay, 6 is smaller, 13, 14, 15, and 16 values. So there's 5 values in the other column that are smaller. Okay, and I do this for each one. So at 20, 18 is also smaller, so there's 6 values. Ties are worth 1/2. So here I've got a 22. I've got 6 values that are smaller and a tie, so that's going to give me 6.5. And at 64, all 8 numbers are smaller, so I write 8. Okay, and then here's 170, so I'm also going to write 8. 190 is 8, and 315 is 8. Okay? So an interesting thing to note is in non-parametric statistics, or in this test, it doesn't matter how big this number is. I could have done 3 billion, and it would still only count as an 8. Okay, we're just kind of comparing how many. So it doesn't matter, a comparison is like non-parametric statistics are like sports, and parametric ones is like business, right? So as far as winning or losing a sports game, if your team loses by 1 point or loses by 50 points, it doesn't matter. It just goes in the records as a loss, okay? If your company, however, had a year where they underperformed and came in, I don't know, like $1,000 lower than what's expected, that's not as bad as if they came in, $1 million lower than expected, okay? So the magnitude actually matters, right? And so when calculating things like the mean, the magnitude really matters. But for non-parametric statistics, the size of this last number, 315, doesn't really matter. It's just, okay? So I do the same thing. I say how many numbers in the other side are smaller. So for 6, 0 numbers are smaller. So actually all of these, I get zeros. And 18, we have 1 number that's smaller. 22, I have 2 numbers that are smaller and a tie, so I write 2.5. And at 29, I have 3 numbers that are smaller. Okay. All right, and then the next step will be sum these counts. Okay, so I add these up. And here, if I add all of these up, I get 49.5. Over here, I get 6.5. Okay, and then what we'll do is we use the larger column total, column sum, as our test statistic, which for whatever reason is called U. So in our case, U is 49.5, right? We have 2 samples. Okay, we have n1 has 7 values and n2 has 8 values. Okay, and so what happens is with these two values, we're going to look these values up in the table, and the larger n is n, and the smaller n is called n prime. Okay, so that means n is 8 and n prime is 7. Okay, so we're going to look up n8, n prime 7, u 49.5. We're going to go to a table. There's a table specifically for the Wilcoxon-Mann-Whitney test. Where am I looking? Reference tables. All right, so here is table 6, critical values and p-values of US for the Wilcoxon-Mann-Whitney test. Okay, so we have n is 7. So we go to this first column over here, n is n, and we go down to n is 7, and then n is 8, and n prime is 7. Okay, so we go down to n prime. Where am I? Okay, n is 8, and then the second column, n prime is 7. All right, and so I'll go ahead and I will copy this portion. All right, so this is the line in the table here. All right, no, that's not what I want. That's what I want. Okay, so here we are, and we are going to we'll look this up. Okay, and my u is 49.5. Okay, so I'm going to go ahead and just paste this here. Okay, so n is 8, n prime is 7, and then u is 49.5. So if u is equal to 50, my tail area is my p-value is 0.0093. Okay, so u is 49.5. It's between 48 and 50. Okay, so u is equal to 49.5, which means if we look at this, oops, okay, the p-values for a non-directional alternative is in italics. So my non-directional p-value is between 0.021 and 0.0093. Okay, so depending on our alternative hypothesis, we had a directional alternative which said the growth area produces larger values than the gap area. Okay, and then we had a non-directional one, and the non-directional one said, well, one of these, I don't know which one, but one of these makes larger values than the other. Right, so if we use the non-directional alternative, our p-value is between here and here. The directional p-value, which I would say is probably the one we're going to use, directional p-value is between, and it's going to be 0.021 divided by 2, which is 0.0105, and 0.0093 divided by 2 is 465. Okay. Okay. So something in between around like 1% and 1/2 of 1%. Okay. So if, let's say, alpha is equal to 0.05, my p-value is less than alpha, and we reject the null hypothesis, okay? And we say, we conclude that we have evidence that the growth area tends to produce larger soil respiration values than that the growth area tends to produce larger soil respiration values than the gap area. Okay, that's the non-parametric test, and that's it for non-parametric statistics. Today's kind of like we're covering just a whole bunch of different sections in the book. Okay. All right. Okay, I'm going to move right along. And we will take a look. I think we'll have time to do a section from Chapter 8, which is really going to be the only section from Chapter 8 that I do. And then we'll probably also get through Chapter 9, or at least some of it. And then I'll probably next week do Chapters 10 and 11, and then the following week we'll do Chapter 12. That will cover most of the textbook. So can't cover all of the, I'm skipping a lot of stuff from Chapter 8, but I think it's okay. We're just going to do kind of one section here. All right, so Chapter 8 introduces the notion of paired data. Okay. And we are going to look at just one test for paired data, and that is going to be the paired t-test for paired data. Okay, and this is it. Okay. If you're interested, more on paired data, you can read the rest of Chapter 8, but we're just going to look at the t-test for paired data. All right, so what is paired data? Okay, so this is different from what we've done in the previous chapter, where our t-tests have independent samples, or independent samples of data, right? So we have, one population, and we have another population, and our samples are drawn, the people or observations we get from sample population 1 have nothing to do with the observations we get from population 2. Okay. In this case, the samples of data are paired. Okay. So the idea here is that each observation in sample 1 is paired with an observation in sample 2. Okay. And so because of that, one necessary thing is that sample 1 and sample 2 must have the same sample size, okay? Okay. So if you have two samples and they have different sizes, you know you're not in a paired data situation. Okay. However, if you have two samples that are of the same size, it doesn't necessarily mean you're in a paired data situation. Like you could be, you might not be. But if you're in a paired data situation, the two samples must have the same sample size. Okay. So common scenarios are before and after measurements. Okay, so every before is measured paired with an after measurement. Okay, you have kind of twin studies and experiments. Okay, and then sometimes you have observations that are paired based on kind of demographics or other traits. All right. Okay, so let me do a silly example here. All right, so we've got let's say we have an advertisement, or someone study for a magic weight loss pill. Okay, I don't know. All right, and we're going to say we have 5 people. Okay, we have person A, person B, C, D, and E. And we're going to get before and after measurements. Okay, so we'll say person A before weighed 250, after taking the pill went down to 245. Okay, before person B weighed 205, afterwards weighs 200. Person C before weighs 180, after weighs 175. Person D before weighs 290, after weighs 285. And person E before weighs 170 and after weighs 168. Okay, so just looking at these numbers, do you think this magic weight loss pill works? It seems like it, right? Everybody who's taken it lost some weight, around 5 pounds. Okay, person E only lost 2, but as far as everyone else goes, yeah, sure looks like it's working. Okay, so I went ahead and I calculated statistics for these made-up numbers here. Okay, so Y bar is 219, S is 50.3, the standard deviation. Okay, here Y bar is 214.6, and S is 49.58. Okay. All right, so let me just write the wrong way to analyze. Okay, is treat the values independently. Okay, so the wrong way would be to say that we have two populations. We have a before population and an after population. And the null hypothesis is that there's no difference between the before mean and the after mean, and that the alternative, we want to see if the after weighs less than the before. So we want to see if this changes as positive, before minus the after. Okay, so if you do this, your test statistic is going to be y bar 1 minus y bar 2 divided by your standard error, which is s1 squared over n1 plus s2 squared over n2. Okay, so if you plug in all of these numbers and you go through this thing, right, so n1 is 5 and n2 is also 5. You got 5 observations. And you do this, you just have to take my word for it. So in the interest of time, I'm not going to go through the number crunching, but you're going to get something like 0.139. Okay? And we would have degrees of freedom would be n1 plus n2 minus 2. We would have 8 degrees of freedom. Okay? And then, if you look this up, the upper tail area, look up t equal to 0.139 in the t-table, and then you get the upper tail area is greater than 20%. Okay, and because it's a one-sided or a directional test, okay, directional test, so we don't double the p-value, okay. Or do not double the tail area. Okay, we get our p-value is greater than 20%. If alpha is 5%, we do not reject the null hypothesis. And we say we do not have evidence that there's weight loss. Is that okay? I just kind of blitzed through the calculations very quickly, but you do this so you get your p-value, and we'd say we don't have evidence of a weight loss. Okay, but this was the wrong way to do it, okay? This is the wrong way to do it. Because if we look at it, it sure looks like everybody who takes the pill is losing weight, okay? So what's going on, the reason why we can't come to this conclusion is that, the starting weights of all of these people, there's huge variation, okay? We start off at, the person who weighs the least is 170, the person who weighs the most is 290, and that's just a large amount of variation. Okay, there's a large amount of variation there, and so a change, like a difference of around 5 pounds or so, okay, 4.4 pounds, that difference is lost given how big the range of starting weights are. Okay, so the shift in weights is not big enough. So what we need to do is we need to treat the data as paired. Okay. So I'm going to go ahead and I'm going to copy this to our new slide here. Whoops, that's not what I wanted. All right, that's fine. Can I just delete this? No. All right. All right, I don't know how to I don't know how to use this. Okay. Oh, all right, I don't know. Never mind. I don't know what's going on. Okay. Just give me a second here. All right, I just want to delete everything over here. Can I do this? Why is this not working? All right, just something's going on. All right, just ignore all of this over here. All right, so what we want to do, can I even erase this? All right, so I want to treat them as actual paired data, okay? So we're going to calculate a difference column. Okay, so the correct way, treat the data as paired. Okay, so we calculate a difference column and we say, okay, before minus after, this person lost 5 pounds, this person lost 5 pounds, this person lost 5 pounds, this person lost 2 pounds. Okay, so we get a difference of 4.4 and a standard deviation. If I take the standard deviation of these numbers, I get 1.342. So the mean difference, which we'll call D bar, is equal to 4.4 pounds, and the standard deviation of the difference S sub D is 1.342. Okay. My hypothesis is about the difference. The mean difference is equal to 0. And then the alternative, if it's one-sided, is that the mean difference is greater than 0. Okay? So note, there is only one mu in the hypotheses. Okay? There's no, we're not talking about two populations anymore. We're not treating the values from before and values from after as two separate populations. We're just comparing before versus after, and we're saying that there's just there's one mean average weight loss. Okay, that's what we're saying here. So we're only looking at the mean difference. All right, and so here our test statistic is going to be T is equal to D bar divided by the standard error. And the standard error is going to be S divided by the square root of n. So this should look familiar because this is the standard error for a confidence interval with one sample, right? And that's basically what it simplifies to. So we ignore the fact, so we have two columns of original data, but we only take the difference and then it becomes just one column, one sample of data. Okay? And we would say something like, you know, if we assumed this null hypothesis were true, if we assumed that the weight loss pill is ineffective and that the difference in weight loss is 0, you know, I would expect my average difference, my D bar, to be around 0. I'm getting 4.4. Is this significantly different from 0? Well, we compare it to our standard deviation. We can see, yeah, it looks pretty significant. So we're going to do this. And my test statistic is going to be 4.4 divided by the standard error, which is 1.342 divided by the square root of 5. And this comes out to be a t of 7.33, which is a really big number, okay? So we look up t equal to 7.33 with degrees of freedom equal to, well, how many degrees of freedom will I have here? 4, right? We treat this as one sample, okay? So degrees of freedom is going to be n minus 1. We're going to have 4, okay? We have one sample, n minus 1, and if we do that, so we go to my t table, 4 degrees of freedom, I look up 7. Okay, so it's between these last two numbers, so that means my tail area is between 0.005 and 0.0005. Okay, so the t is between, I think it was 4.6, 4.605, between 4.604 and 8.610. Okay. So the p-value is between 0.005 and 0.0005, and therefore we will reject the null hypothesis, come to the conclusion that this magic weight loss pill actually is effective. All right. I could just apply the eraser. Here's my, I don't know why this is not, okay, brush, eraser, oh, I could have done that. All right, that's all right. It's a little excessive. All right. Is that okay? So that is that's going to be it for chapter 8. Chapter 8 covers more paired data. It looks at some non-parametric tests for paired data. Again, you know, the most common scenarios for paired data will be before and after. Okay, so if you're in a before and after situation, you'll have paired data. And then sometimes, you know, they want to do studies and they want to compare one population versus another population, or two different groups, and they want to say, like, okay, you know, we want to compare students in this school district versus this school district, and then they try to match up each student by saying, you know, this student, you know, it comes from this socioeconomic class and had this test scores before, and we're going to pair them up with somebody similar in the other school districts, and so you might have something like that. Okay. And again, in both cases, you are not treating them as independent samples of data, but you're only going to look at the difference between the two groups. The difference. Okay. All right. I hate to do this to you guys a little bit, but not really. I'm going to just start chapter 9, okay? And this is like an entirely new concept, a new topic, and I probably won't get through all of it. I'll probably have to wrap up chapter 10 next week. For the homework, I've assigned some problems from chapter 10, but don't feel like you have to do them, okay? So, like, do what you can. Review the other problems from chapter 7. Next week's quiz really only covers chapter 7 and chapter 8, okay? This chapter 9 stuff will not be quizzed next week. It'll show up, in the future and on the final. But just trying to squeeze everything into the weeks that we have. Okay, everything we've done so far, confidence intervals and this t-test stuff and even the Wilcoxon-Mann-Whitney test, everything's been a numeric response. Okay, so we've been looking at things like, the soil respiration, which was a number. We looked at like how heavy the carrots were. Okay, that was a number, right? Sometimes we have a categorical response, okay? So sometimes the response variable is a categorical variable. Okay. So categorical response variable will be, something's in this category or it's in a different category, or we're talking about like the color of the car and it's either silver or white or black or red or something. We're looking at some kind of categorical response variable. Okay, so the first thing we can look at is we can create a confidence interval, but it's going to be for the proportion that belongs to a category. Okay, so we're going to do confidence interval. Or for the proportion, in a given category. Okay, and this is best for what we consider dichotomous data. Okay, which means there are only two categories. All right, so either yes, yes or no, basically, okay? And again, the idea here is you've got, as always, the general picture is you've got some big population, and the population is too big for direct observation. Okay, but in the population, some proportion P belong to a certain category. Okay. Right. So it's, what proportion in the population, supports this particular candidate, okay? So, maybe in the, if we could freeze time and know the answer, it might be like 34% of the population supports this particular candidate or something, okay? So there's some number P there, okay? But we can't study the population directly, so we take a little piece out of it, and this is our sample. Maybe we call 100 people, and we ask them, do you support candidate so-and-so? Okay, so we observe a sample. Okay, the sample has the observed proportion p hat. Okay, so this is the proportion we observe, which is going to be y divided by n. Okay, so y will be kind of the number of yeses and n is total sample size. All right, and we want to create a confidence interval for the of plausible values for the population proportion p. Okay. Okay, and so this is basically, again, during election season, they'll say, so-and-so is polling at this number with a margin of error of this, okay? And that's basically a confidence interval, right? That margin of error is that plus or minus part, okay? Our textbook uses what's called the Wilson adjusted sample proportion. And I have to say our textbook is kind of unique in doing this. Most textbooks don't. Most textbooks just use p hat straight, but our textbook uses the Wilson adjusted proportion. And they call this p tilde. And what they do is they add 2 to the numerator and add 4 to the denominator. So why would they do this? Okay. What this does is it helps avoid having situations where you get extreme proportions like 0 or 1. Okay, so if you're on a mission to search for something that's extremely rare, okay, you might often get, you might survey 100 people and nobody answers yes, everybody answers no, okay? And in that case, your p hat is going to be 0. And if your p hat is 0, then you can't make a confidence interval because it just doesn't work. So, so by adding 2, you make sure your numerator doesn't end up 0. Okay, but then also by adding 4 to the denominator, it also avoids the situation where you get 100%, right? So you might have another question and everyone answers yes, okay? So you add 2 to the numerator, but you're adding 4 to the denominator, so you end up in a situation where you don't get 100%, okay? So this avoids p tilde equaling 0 or p tilde equaling 1, which causes problems. Or I should say which would cause problems. Yeah. All right. Okay, so if you have this, then the 95% confidence interval is going to be this adjusted proportion plus or minus 1.96 times p tilde minus 1 minus divided by n plus 4. All right. I feel like we've covered confidence intervals enough that I don't have to like plug in numbers, work through it, and give you all of the interpretations again, right? Like, so, the interval you create some interval and you can say, do we have evidence that the proportion is, I don't know, different from 0.8? And then you just see, is that number within my interval or not? So the same, like if you understand confidence intervals for the population mean mu, then they work the same way here, okay? Except rather than talking about the mean, we're talking about the proportion in the population. Is that okay? All right. Okay, so that's one way we can handle categorical variables, is we just kind of turn them into proportions and then we make confidence intervals based on that. Yes, question?
So somehow just referring to the table, the assumption is that in this situation there's infinite degrees of freedom?
Yeah, it's So yeah, what we are assuming is that with a proportion, we're basically doing a normal approximation to a binomial situation is what we're doing, okay? Is that because when you have a yes and no situation, you can also kind of frame it as like this binomial dichotomous situation. And then, and if you have kind of a big enough n, then the binomial can be approximated with the normal, okay? And we never tried to approximate the binomial with a t distribution or something like that, okay? And so basically, yeah, we're using this 1.96 because at the heart of it, we're approximating what we consider to be like a binomial with the normal, okay? Except we're looking at the proportion rather than the count. Okay. But don't worry.
Just it's always 1.96.
Yeah, it's always going to be 1.96. For the 95% confidence interval, it's always going to be 1.96. Okay. Okay. All right. And then the other kind. So that's great and all if you have just kind of this dichotomous yes and no situation. And then the other kind of situation we might find ourselves in is where we've got several categories, all right? And so now I'm going to introduce the chi-squared test for categorical data. Okay. Chi, it looks like chi, but it's pronounced chi. It's the Greek letter for x, and it looks like, I don't know, it looks just like a fancy x, I guess, okay? Chi-squared. The first one we're going to look at is going to be the chi-squared goodness of fit test. It's a weird name. Okay. Goodness of fit is asking how well does our data fit our assumptions, I guess. Okay, how well does our data fit the assumptions? But I guess they had to make a noun out of it, and they felt weird saying wellness of fit, which sounds thing, but goodness of fit also sounds strange. So, you know, is there a noun version of the like how well something performs? Quality of fit, I guess. That probably would have been a better name, but whatever. Goodness of fit it is. Okay. Okay. So the chi-squared goodness of fit test. We're basically asking, you know, how well does our data fit our assumptions? Okay, so what are the assumptions? Okay, So basically, we have one categorical variable. So in chapter 10, we'll look at two categorical variables, but we're going to say we start off with we have one categorical outcome variable. Okay. And our assumptions are, in our mind, we have proportions of each category. So in our mind, we are expecting a certain proportion for each category. Okay. So okay. And so basically, when we write our hypotheses, it's just going to be a list of expected proportions. Okay. So let me do an example here. All right. Okay. So this has been a long time since I ever took a bio class, but you have like these. Are they called Punnett? How do you spell Punnett square? I don't know. Something, right? You have this. Thing, and you have big A, little a, or something like this. Okay. I don't even know if I'm doing this right. Okay. And I know like big AA and A little a, like they both show the same dominant trait or whatever. Okay. But, you know, according to this model, okay, I guess 25% have AA, 50% have A little a, and 25% have little a, little a. Is that right? Okay. I think. I'm not sure. Okay. And so if our model is correct, okay, right? So this, if we believe this is the model, then we should observe these proportions in kind of the progeny of whatever, you know, we're like breeding, I don't know, peas or something, right? Okay, so we should observe this in our sample of data, right? So our model is correct. We should observe these proportions in our data. Okay, so my null hypothesis is just a list of these proportions. The null hypothesis states that the probability of observing big A is 0.25. The probability of seeing big A little a is 0.5. The probability of seeing little a is 0.25. And then the alternative hypothesis is at least one of these proportions is wrong. Okay, this is if you have more than two categories, it will always be non-directional. Okay, so that's what we have for the hypotheses, and then so this is what we do. Okay, so we look at our observed data. The observed data, somehow we go and we do this, and okay, so we say big A, big A. We get 45 of these. Big A, little a, we have 106. Little a, I get 49 for a total of 200. Okay. Here I'm going to write the expected counts if the null hypothesis is true. Okay. So in total we have 200, and if the null hypothesis were true, I would have 200 times 0.25. I would expect to get 50. 200 times the null hypothesis says 0.5, I would expect to get 100. And 200 times 0.25, I would expect to get 50, right? So I'm expecting to get 50 and I got 45. I expected to get 100 and I got 106. Right? And so the question is that difference in counts, observed counts, is that significant? Okay. All right, so basically the expected counts are going to be your total n times the proportion from the null hypothesis. Okay. All right, and so so we go and we say, all right, well, let's test if this is okay. So the chi-squared statistic is known as the sum of observed minus expected squared divided by expected, okay, summed across all categories. Okay, so I do it for big A, and I observed 45, I expected 50. I square that number and I divide by what I expected, 50. Okay, and I'm going to do this for all of my categories, and I've got 3 of them. Big A, little a, I observed 106, I expected 100. I square that and I divide by 100. And then I do it for the last one. I observed 49, I expected 50. I square that and I divide by what I expected, 50. So this ends up being something like 25 over 50 plus 36 over 100 plus 1 over 50. Okay, so I get my chi-squared is 0.88. Okay, the degrees of freedom here is going to be equal to the number of categories minus 1. So here my degrees of freedom is 3 minus 1. I have 2 degrees of freedom, and I will go to my chi-squared table, and I look up df equal to 2, chi-squared equal to 0.88. Okay, 2 degrees of freedom, 0.88 is smaller than my first number, 3.22. So my tail probability is greater than 20%. Okay. Okay. And for a non-directional test, my tail probability would be my p-value. Okay, so the p-value is greater than 20%. We do not reject the null hypothesis, and we say our data does not provide evidence that any of the hypothesized proportions are wrong. Is that all right?
How do we know that the p-value is greater than 20?
Okay, so that's from the reference table. Okay, so my p-value or my chi-squared value was 0.88. So I say, well, where does 0.88 fit in this row for 2 degrees of freedom? It's smaller than 3.22, so therefore my corresponding tail area, which will be my p-value, is going to be greater than 20%. If my chi-squared was something like 6.3 or something, then it would be in between here and here, and then my p-value would be between 5% and 2%. Okay, that was a lot of stuff that we covered today. So we'll call it there, okay? And you guys have a good week. And we'll see you guys next week. There's going to be a quiz covering chapters 7 and 8, and then and I'll probably wrap up chapters 9 and 10 next week, and we'll also do chapter 11 as well. All right, have a good week. We'll see you guys then.